Hello everyone, welcome to my channel, and we have something new here. We have a lot of circuits here. And as I see, our first circuit. This is a buffer gate. The switch is connected to the base, 12-volt supply. And the LED is taken to the collector side as the out. Hitting the switch. So you have seen here, when you press the switch here, LED turns on. Transistor operates in saturation mode. Another buffer gate here. This is also buffer gate. Transistor switch 1.0. The LED is connected in series with the supply. The input side is in the base. The switch is connected to the base and still working. The transistor switch 2.0, and now the LED is connected to the collector side. 222A transistor, the switch input is in the base, 22 kilo ohms. Pressing the switch. It's also a buffer. Let's see, another buffer here. Made up of almost the same. Switch 3.0. Now, the LED is connected to the emitter side with a, what's this? A parallel resistor. This is a buffer, 27 kilo ohms. The switch source in the input side to the base. This is also a buffer. Again, we also have another buffer here. Transistor switch buffer gate, 5-volt supply. Now, again, the LED is connected to the collector, the switch again, to the base side, and I connected a resistor into the switch and into the base, and we have a resistor at the emitter. Still working. Another buffer we have here. This is also a buffer. Transistor PNP buffer gate. We have the power on LED, and this is a PNP. The emitter side connected is the LED. Current flows to the base and to the collector to the emitter. Then pushing the button here. We get now a total of 6 buffer gate. And now for our latest buffer gate, made up of a transistor logic. Since these 6 buffers are made up of transistor logic, or RTL technology, we have now this, a TTL buffer gate, made up of a transistor in TTL logic gate configuration. Every time we press the switch here, input LED turns on, and at the same time, output LED turns on. This is a buffer gate. 3 transistor. Our input switch is now connected to the emitter side of the first transistor. And this is now the input LED connected to the ground with the current limiting resistor, base resistor of the first transistor. And this one now, the base to the collector of the first transistor connected to the second transistor. The base, emitter, and then this collector resistor of the second transistor. We have the emitter side of the second transistor is connected, is the base of the third transistor. We have the resistor emitter here, and in the base connected to the emitter side of the second, and we have now here the output LED connected to the collector of the third transistor. I'm using 2N3904 and powered by 5V supply. So that is now my collection of buffer gate. I get this 7 buffer gate, including this one, my latest buffer gate. If you're interested on how did I design the circuit, let's move on to the circuit diagram. We have the voltage supply 5V, connected is the LED D1 and then the resistor. This is now the input side. Now this time the emitter side now is where we're going to connect the input. We have a base resistor here, another transistor, and then the RC collector, emitter, and then the output, and then the power LED. We are using this transistor in the diode function mode or reverse mode of operation, connected to the base of the second transistor. And what is the configuration of this second transistor? It is a common collector or an emitter follower configuration. This is the input side. Output side, at initial state, current flows into the RB1 to the base to the emitter, and then to the RD1 and to the ground. So at this state, we got a logic 0 or low level because the switch is open. Current will not flow here because it flows directly to the ground. So we got the first KVL, VCC RB1 transistor 1 BE to RD1 to the ground. We get 4 points, 35 volts, the sum of the two voltage drop at the base and in the RD1. We cannot solve the values of the resistor here since we're trying to solve all the values of the resistor here because we have two unknown. Now current also flow here. Why not current flow here? Because this is cut off. Since this is grounded, flows into the power LED, making an KVL at VCC, RD3, then D3, and to the 0 volts to the ground. KVL, transposition, substitution, we got the voltage drop at RD3, 3 volts. Using Ohm's law, VIR, RD3, 3 volts divided by the current rating of the LED to turn on, 0.02. And from the data sheet, we got the resistor value of RD3, 150 ohms. But I'm using 220 ohms, my available resistor. Let us consider this figure, applying a pulse or hitting a switch or pressing the button. So when you press the button here, input LED turns on because the current flows into the R1, D1, to the RD1 to the ground. Also, the current now flows into the base RB1 to the base to the collector and to the base to the emitter of the second transistor. The first transistor, why is it not flowing here? Because when you press the button here, it will give a positive potential or high level to the emitter and making this emitter base to emitter junction to reverse bias, so the current now will flow into the base collector. This is the reverse mode function of the transistor. and this is connected to the base and to the emitter side of the second transistor, so making the current to flow, forward biasing now this transistor. So when this is forward bias, current now flows into the collector to the emitter. Voltage output is equal to voltage input. This is the voltage input. VCC minus the voltage drop at RB1, voltage drop at the BC, base to emitter. That is now the base input, BI. So first, we're going to turn on the transistor to compute for the base input from this point to this point. We got the KBL, VCC, RB1, Q1 BC, Q2 BE. We got now by substitution, transposition, calculation, since we know that the BC, there's a voltage drop at the base to collector junction of this transistor, since this is in forward bias, and it has a voltage drop of 0.7. To turn on that 0.7 volts, we got the voltage drop also 0.7 or 0.65 in the case of this 2N3904. So we got now this BC, BE, 0.65, 0.65, 5 minus 3.7 volts. That is the voltage drop at the RB1, KBL, up to this point. Why is it that up to this point? Because we want to know the voltage input. Still, we're not including this voltage output. We are considering this voltage input. We are calculating the voltage input. Whatever the voltage appearing into the base resistor now is the voltage input, which is 3.7 volts. This is now our voltage source, the voltage input to the load. Voltage input now is 3.7. This is green, is the voltage input, which is now the supply to our load. Voltage input, this green line, minus the voltage output or the load voltage. Voltage output here is equal to the voltage at the resistor emitter. Using KBL here up to the ground. So we know that voltage of the RE is equal to 3.7 also, because this emitter follower, whatever the input voltage is equal to voltage output. So we know that the voltage here, voltage at RE, is equal to the voltage input. Why is it that I'm computing up to here? When you forward biasing the transistor here, the current now flows into this side. In the datasheet of the 2N3904, it is capable of switching up to 100 milliamps of collector current with the HFE of 100 that is given in the datasheet. So for computing now, we need to compute for the value of IB here, base current. We need that current by current gain formula, IC over IB. Since I'm not setting the current. This is actually given into the data sheet of the transistor, 100 milliamps. It is capable of delivering 100 milliamps or capable of switching up to 100 milliamps into saturation. So if that is in the case of that, by substitution, 100 milliamps IC over 100, the HFE by current gain. Since 100 milliamps equal to 0.1 ampere divided by 100, we got 0.001 ampere or 1 milliampere. That is now the base current. Why did I just compute that this way? Because this is still in input side of the circuit and this is the output side. We now know the value of the resistor here by using Ohm's law. We know the voltage drop at RB1 3.7 divided by 0.001. We got 3,700 ohms, 3.3 kilo ohms. We have another KVL here. BCC, RC2, and the voltage at the collector to emitter. to the output side. Since we know that in saturation, the collector to emitter of this transistor is 0.3 volts using the KBL, because now this transistor is in forward bias, making the current to flow into the collector side. We got 4.7 volts at the output side. Using Ohm's law, it gives us 47 ohms, or I'm using 100 ohms available resistor. We need to use the resistor here. It's a coupling resistor to know the current at the collector. 5 volt supply. Now when you hit the switch, current flows into the D1 to the RD1, making a KBL here to the ground. Using the KBL, we got VCC, VD1, RD1, and we got the voltage drop of RD1 3 volts. Since we know that the voltage drop there and the current rating of the resistor of the LED, we get 150 ohms, 220 ohms for the KBL when you press the switch here. So we get now the value of resistor here. Since we know this type of formula, transistor formula, IE is equal to IC plus IB. IE, the current at the emitter, is equal to IC plus IB. So we know that collector current, which is 100 milliampere plus 1 milliampere base current, we got 101 milliampere or 0.101 ampere. Using Ohm's law, voltage at RE is equal to current times resistor, Ohm's law. Since we know the voltage drop at RE here, 3.7, and the current flows is the current at the RE. Why is it 101? I'm considering this current to flow into the load without a load, or into this emitter without a load. The total current that flows is, computing that without the load, 36.63 ohms. The total resistance now is 36. I'm using 100 ohms. Without the load, you need to compute for the value of the resistor here. If you have a resistor here, we need to have a resistor here, because this is our output or the load resistance or the output impedance. The output resistance, we need to connect a resistor here, and the current that flows here when the transistor is forward bias is 100 milliamps, the current rating of the transistor in switching application of this type of transistor. 100 milliamps total current without a load. Computing that without a load, we got 100 ohms. Now we know the value of resistor, 100 ohms. We get this voltage output is equal to the voltage of the emitter or RE or input and the RB1. They are all equal. Voltage output equal to the voltage input and the voltage at the RE. Okay. Since in parallel, voltage output is equal to the sum of the two voltages, voltage drop at RD2 and the VD2. Or you can take a KBL using the technique of KBL, voltage output minus a voltage drop minus a voltage drop, VD2 2 volts, and we know that the voltage output got a 1.7, the voltage drop at the RD2. Since we know that RD2 voltage drop 1.7 times the current rating of the LED, we got 85 ohms, but I use 100 ohms, so we got the value of 100 ohms at the RD2. And this is now our new circuit from this. Why did I change the circuit, this circuit into this circuit, instead of just, as you have seen here, total current here is now divided into the RE and into the load. That is the case of that. Instead of just using this, I'm putting now this constant current source because of the variation of the current of the IV and the switching of the transistor and the thermal junction of the transistor makes to vary the current that flows into this junction or into this node. So in order to get the constant current, we need to use another transistor. The output is now into the collector. See this? Instead of simple LEDs series here circuit, I'm now using a transistor in replacement in order to have a constant current source to the LED. So whatever the variation of the base current here, still we're getting a constant current for the LED. This is now served as the current driver for the LED. We have a constant current source for the LED. In any case of variation of base current here, since this is the total current that flows 100 milliamps minus the base current, and then the other current will flow into the resistor emitter resistor, division of the two current because they are in parallel. Since we know that the LED consumes 20 milliampere to turn on, so it means the current that flows here is, okay, IE is 0.101 ampere. That is the total current without the load. See that? Without the load. Now, but with LED output, current now divides. So IE now, the IE is equal to current at the RE plus the base current of the transistor. Now, using the current gain formula, since we know the current collector current is 20 milliampere in the case of LED, or 0.02 ampere divided by the HFE 100, we get the base current of 0.2 or 200 microampere. And now if you're going to compute for the values of the current at the emitter resistor, you get 0.1008 ampere. The current divides. Very small current. KBL at BCC to RD2, D2, Q3, C is set. So we're taking another KBL here to compute for the values of the resistor. RD2, BCC, RD2, D2, collector emitter saturation. BCC, RD2, D2, collector emitter saturation, 0.3 volts. We got the voltage drop at RD2, 2.7 volts. Using Ohm's law, IR, RD2 transposition, RD2 135 ohms. I'm using 220 ohms for the value of the resistor at the collector side of this new transistor. So this is now the TTL Buffer Gate. I'm using this schematic diagram. I have the power header plus minus 5 volts and also an input provision. If you're trying to connect a clock, we're going to connect a clock here at the input. Also for the output, if you're going to connect the onboard or just an external output. Onboard for the test lamp and external output. And this is now my layout for the circuit TTL Buffer Gate. So that is the operation of this TTL Buffer Gate. No input, no output. Input without buffer gate at TTL technology, and is still using this technology today that exists in the form of IC packages or integrated circuit, usually found in IC manufactured by Texas TTL. No input, no out. With input, with output. Okay. Thank you for watching the video.